Okay, so as I mentioned, we're going to do a little bit of lecturing here, do a couple examples maybe, and just keep us on pace and all that good stuff. So right before we finished off there in lecture, we were talking obviously about how to do equilibrium calculations. Again, we use a ICE table to do that. And again, that's initial, change, and equilibrium. And really, it is the change part that we represent with an X. It's kind of the most important part here. That is ultimately what we're trying to solve for as we go through these problems. That's going to allow us to get to our equilibrium concentration. So as we mentioned before, one way that we can kind of do that is through the quadratic. And we have ax squared plus bx plus c equals 0. Again, or minus b plus or minus square root b squared minus 4ac divided by 2a. I would say in terms of complications, that would be the most complicated way that we could solve for it. We will talk about some other ways along the way as well. And as we talked about before, the ultimate goal here is to find an x value that will obviously give you a positive value when you put it back into that equilibrium line, and will get you your equilibrium concentrations. So again, we could do this with, as mentioned before, we could do this with pressures and a Kp value. Once again, does need to be in atmospheres, works exactly the same way. Again, we want to make sure we use our coefficients as the numbers that come in front of the x's, as that will definitely determine the stoichiometry that we need for this situation. So earlier, again, we did have something like this. I think I forget what it was, but we'll just write something like this, right? And remember that the one that we looked at earlier there was we had some numbers for our reactants. And again, we did not have numbers really for our products. And we did assume that it was 0 to start with, which is a safe assumption if you're not given any information about your products. Now, if you are given some information about your products, let's just say they also said, hey, you started with 2 molar of this guy as well. What you would definitely want to do in this case is this would be the second situation where you would want to perhaps calculate Q. And we could calculate Q in this case because we do have everybody's concentrations. Why would we want to calculate Q in this situation? Well, it's probably not for the answer of are we at equilibrium, because if you're doing this type of problem, you're probably not at equilibrium. Otherwise, it's not much of a problem, right? So really the reason we would want to calculate Q in this case is for the direction of the reaction, right? So if we calculate Q and it tells us we need to go to products, we know we are going in this direction. What that would affect in the table is the change part, right? So if we're going in this direction like we did in the example before in class, these guys would be minuses and these guys would be positives. But what would happen if we, for some reason, calculated Q and it said, hey, you need to go that way to reach equilibrium? What would happen to my change part? Well, if the reaction is heading from products to reactants, my products are actually decreasing, right? And my reactants are actually increasing, yeah? So this would be the second situation where, outside of it, just a straight sort of Q type problem, that you may want to calculate Q just to verify which way this reaction is going. Since you obviously already have some products, you got some reactants, so this reaction is moving. You want to make sure you know which direction it's going to actually be going, as it could affect it. Now, probably not, but in a lot of cases, if you forgot to calculate Q, maybe in this situation, you probably would be okay. Switching back and forth. Push that in here. All right, so again, this would be the second situation where you might want to calculate Q just to verify it is going, the way you think it is. All right, so let's take a look at one here together. Right over here. Go this way. All right, so we have this reaction here. Br2 goes to 2Br. The Kc for this is 7. And we have an initial concentration of Br2 of 0.663 molar. We want to know what is everybody's equilibrium concentrations. So we would definitely be doing an ice table in this situation. So we could write our equilibrium expression, and our K in this case would be the concentration of Br, and we again would need to square it because of the coefficient. We would divide it by the concentration of Br2. Coefficient is 1, and that would equal lucky number 7. I guess we'll see how lucky it is in a second. We need a calculation. So we're going to set up our ice table here. So we're going to go with our Br2 to our 2Br. Initially, we are only given our concentration of the Br2, which is 0.663. And again, if you're not given any information about your products, it again is safe to assume that it is going to go to the right there. All right, you start with 0. Also, as I just mentioned, it is safe to assume that because we only have reactants, we should expect this reaction to head towards the product side. That means my minuses will be on the left there and my pluses will be on the right. So this would give me minus x and plus 2x. Again, we want to make sure we do use the coefficients there. As we talked about earlier, that's going to take care of the stoichiometry part of it and make sure you have the right mole to mole relationship in this reaction. We're just going to carry everybody down here. 0.663 minus x and 2x. Any questions on the ice table here? All right. Like I said before, at this point, the goal really is to solve for x. So we want to take everything we got on the equilibrium line, basically, and put it into our expression. And if we do that there, that's going to give me 2x up on top, and it does need to be squared. We're going to divide it by 0.663 minus x is equal to 7. So we do need to solve for x here. So we do need to kind of get everybody together on one side. Probably the first thing you're going to do is multiply this whole thing on the bottom to the other side. And if you do that, by the way, I'm also going to square the top there. That's going to give me 4x squared up on top. That will now equal 0.663 times 7, which is 4.641 minus 7x, right? So remember, we do want to get this in the form of that quadratic. So I'm going to bring everybody to the same side. It really doesn't matter which way you go. I will say most people roll with the x squared being positive, but it doesn't really matter. So I'm going to bring everybody on this side back to that side. That means I'm subtracting the 4.64 and I'm adding the 7x to the other side. That's going to give me 4x squared, glare on this side here, plus 7x minus 4.641. And that's going to equal 0. That is going to be basically my A, B, and C in my quadratic. By the way, for C, we do take the negative, yeah? So we do take that negative with it, right? Along the way. So we're going to go into our quadratic here, which is x is equal to minus b plus or minus the square root, b squared minus 4ac divided by 2a. All right, so we're going to go into our quadratic here. No more technical difficulties, hopefully. All right, so we're going to put it in there, and I'm going to go with, we got minus 7 plus or minus the square root. And if we do everything inside the square root, which is, in this case, 7 squared, minus 4 times a, which is 4, times c, which is negative 4.641. That should give you inside the square root, before you take the square root, of 123.256. You then can square root it. And I'll get you something like 11.10, all divided by 2 times A, which should be 8 if I do it without the calculator there. Once again, this is going to give us our two X values. I'm going to do the plus first. So we're going to go minus 7 plus 11.10 basically, divided by 8. Going to give us an X value of 0.513. I'm going to do the minus now. So minus 7 minus basically my 11.10 divided by 8 will give me a negative 2.263. 0.263. That works. Any questions so far on that? Yeah. I decided in this case because it was pretty much decided for me in the sense of the problem. We were only given reactants and we had no products to start with. So because you only had reactants to start with, the only direction that reaction could proceed is in the forward direction. Yeah. So that's why we'll be losing our reactants versus our products. Yeah. Other questions? All right. Now that we have this, obviously we want to pick the X value that's going to help us here. That X value is going to go into this spot here on our equilibrium line. And you could probably just see from looking at the number here, this one is not going to be so great because if I take 2 times negative 2.263, I'm going to end up with a negative number, which you cannot have a negative concentration. So this would not be obviously the best choice here to use. That will leave us this guy here, which would be a good choice to use because that should give me some positive numbers. So at this point, I can now put my X value back into my equilibrium line. And for BR2, I will see it is 0.663 minus my X value of 0.513. And this is molar since it is a concentration. We do need some units there. And that's going to get us I believe, 0.150 molar. We could do the same thing over here for our BR. Our BR in this case at equilibrium is equal to 2 times X. So that would equal 2 times 0.513. And that's going to get me 0.513 times 2. We'll call it 1.03 molar in this particular case. First off, any questions on that calculation? Now, perhaps one of the nice things about this, since it is math, you like math, I suppose, right? If it is math, can I check to see if I didn't screw up somewhere? How can I check? Well, what I just calculated was my equilibrium concentrations, right? So if I take my equilibrium concentrations I just calculated and put it into here, what number should it equal? 7, right? And it may not be perfect on 7, but it should definitely be in the 7 ballpark. And if you do, I think you got like 7.0 something. Obviously, with some rounding, it's not going to be perfect. But if you put it back in there and you get 124, you definitely screwed up somewhere. Yeah. Or 0.22 or something like that. So, it's a good idea at the end of these to check just to make sure you didn't kind of mess up. This wasn't terribly difficult quadratic, but there are some where there's a lot of numbers moving around. And, sometimes people mess up on like adding or subtracting. So it's a good idea at the end, to pop it back into that equilibrium expression. And it should be fairly close to your equilibrium constant value. Again, it won't be maybe perfect, but it should definitely be pretty close. Just a little bit off with probably some rounding and stuff that you did. Any questions on that there? All right. Zoom in case you missed it. All right, well, I did one. Why don't you do one? So we have a mixture of 0.5 moles of H2 with 0.5 moles of I2 in a 1-liter flask. What are the equilibrium concentrations, everybody, if the K value is 54.3? So take some time here, work it out, see what you come up. Okay, let's take a look, see how you're doing on this one. Again here, we have some moles given to us and some volumes, so we can get some molarity. So obviously here our concentration, maybe something to write with would be good too. Let's try that there. Maybe not the highlighter. I'll go down. All right, so our concentration here of H2 would be our moles, 0.5 moles over 1 liter. That's not too bad. That's 0.5 molar. Same thing here for our I2. It's going to be 0.5 moles per 1 liter, 0.5 molar in this case. We could write our equilibrium expression for this, which would be concentration of HI. Once again, we do need to square it because of our coefficient, divided by the concentration of H2 and the concentration of I2, and that equals 54.3 here. All right, so we're gonna do an ice table, and I'm just gonna flip the page here so I got a little bit more room to write on, I think. There we go. I'm gonna borrow that. So initially here, we do have 0.5. We got 0.5. And again, nothing was mentioned about our products. So we could assume that it is 0. And again, our K is this H2, our I2, and 54.3. That means that we could again safely assume we are heading in the product direction there. And that means we will have a minus x here, a minus x here, and again a plus 2x because of our coefficient. That is going to get us at equilibrium 0.5 minus x, 0.5 minus x, and 2x. Any questions so far? Just like previously, the goal here, right, is to solve for x. So we're going to take our equilibrium line basically and put it into our K expression. That's going to get us here, it looks like 2x squared up on top, divided by 0.5 minus x, 0.5 minus x, and that's going to equal 54.3. So again, the goal here is to solve for x in this case, and hopefully you recognize, and they call that like a perfect square on both sides. You can put a big old square root on both sides. And if I square root the left there, I get a 2x. If I square root the left bottom, 0.5 minus x. And the thing personally I forget to do most of the times, actually square root the 54.3. And that's going to get me 7.36885. We also want to, as we go through these problems, think about how we can make our lives easier sometimes. Yes. So, if there's maybe an easier, maybe we can't. If you like quadratic, you could definitely roll with that and do some bunch of factoring and a bunch of stuff there. But why do that if you maybe don't need to? Yeah. So we're going to multiply that to the other side there. That's going to give us 2x is equal to 0.5 times 7.36885. 3.6844 minus 7.36885x. I'm going to bring my x's to the same side, so I'm going to add that back to the other side. That will essentially give me 9.36885x is equal to 3.6844. We're going to divide now. And we will end up with here. It looks like something like 0.393 as our x value. By the way, if you quadratic it out, you should get basically the same number. So you could always quadratic if you want. But as we will see, as we see in this problem, there are sometimes a different way to solve it. It might be a little bit easier in a time crunch situation. But just like there's an easier way to do it sometimes, sometimes the only way to do it is quadratic. So again, it kind of goes both ways. So that is our x value that we're going to put into here for each of these. And that would get us here for the concentration of H2. It would equal 0.5 minus 3.93. 3.93. I guess I could go 0.5 first minus that would get me 0.5 minus 0.393. Going to get me 0.107 molar. Obviously, here our I2 will be the same. 0.5 minus 0.393, 0.107 molar. And lastly, here our HI, I'll just come up here. Our HI is equal to, at equilibrium, 2x. So that's going to be 2 times 0.393 molar and 2 times 0.393. Going to get us a 0.786 molar in this case as our product side there. Any questions on that calculation? Again, if you put those numbers back in, you're at about 54-ish. Yeah. I think I'll come to you next. No problem. Yeah, no worries. Yeah. Can you use the quadratic instead of doing what I just did? Is that what you're asking? Or yeah, you can. Yeah. So you could always do the quadratic if you want, and it should give you the same answer. So if you're more comfortable doing that, you can. But again, time-wise, sometimes it might be easier to do some other things along the way. Did you have a question in the back? Can you always use the square root? No. So it does have to be a perfect, in this situation, it does need to be a perfect square on both sides. So if you so for example, I don't think the last one had it, but um if it's not a perfect square on both sides, you can't do the square root. So it only was a perfect square because these two are identical, right? And basically that's 2x times 2x, which is identical. So that's what makes it a perfect square. And if it's not, so for example, if this guy was like 0.897, then it's not. Yeah. So, if this guy here was like 0.897, then it would not be a perfect square or anything like that. Yeah. Yeah. Yep. Yeah. The square does come from the coefficient. So this square is for the coefficient, it comes from the coefficient for there, and also when we do the change part as well, yeah. And again, these were ones, which is why we didn't really put anything there. Yep. Other questions? Yep. Okay. All right, let's try one last one here for today, I think. Same equation, same reaction, different stuff going on. 0.00623, 0.00414 molar and 0.0224 molar for H2, I2, and HI respectively. K is still 54.3. What is everybody's equilibrium concentrations? This will test your math skills, perhaps. Okay, let's talk about this one and see how you're doing, how you're progressing, hopefully in the right direction. So we have the same equation and K value that we were looking at in the previous problem. This time, though, we are given some concentrations of everybody here. And that perhaps should trigger to you that maybe you should calculate Q. So Q would be actually a good thing to calculate in this situation. Again, you have the ability to do that because you were given the kind of initial amount to everybody. So you don't really know, perhaps, if you're at equilibrium, you need to reach equilibrium. Again, I would guess that you need to reach equilibrium. Otherwise, it wouldn't be much of a problem. But it will also, again, as we talked about, sort of assure you that you are heading in the right direction in terms of your minuses and pluses. So we'll calculate Q here. Q is, again, calculated the exact same way as we calculate K. So we'll take HI squared, we'll take H2, and we'll take I2 here. We'll put in our concentrations that were given to us. So that's going to be 0.0224 squared divided by 0.00623 and 0.00414 in this case. And this will get us here 0.0224 squared divided by 0.00623 and divided by 0.00414. That gets us like a 19.4 is our Q value. That means in this case, again, Q is actually less than K. That tells us it's not at equilibrium, which probably wouldn't be much of a shock here. But it does confirm for us that this reaction, in order to reach equilibrium, again, needs to go to our product side. So we'll have our minuses on the correct side here, the left side, and our pluses on the right. If you blew right by this, you're lucky, right? But you probably get lucky in a lot of cases. But it's a good idea to do it just to make sure you aren't going in the opposite direction. All right, now that we did that, let's get into the actual problem, which is we're going to do our ice table here. There we go. So we got H2 plus I2, a little 2HI here. And initially here, we have our 0.00623 or 0.00414. And again, in this case, we actually do have a product initial concentration of 0.0224. Hence why we did calculate Q in this case just to verify for our change that it should be going minus X, and we know again we should be heading in this direction, plus 2x. So as we come through here, we're going to bring down 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. By the way, a reminder that is a plus there. People at this point are so used to going minus x that they kind of throw a minus in there for fun. But remember, it is a plus. At this point, first off, any questions on the table here? At this point, we're going to go into our expression, right? So our expression will pretty much be the same as our Q expression there. So we're going to have our K is equal to our HI squared divided by our H2 and our I2. And obviously there, that's going to equal 54.3. Putting in our numbers here, we're going to get a 0.0224 plus 2x that's going to be squared divided by 0.00623 minus x and 0.00414 minus x. And again, going to equal 54.3. So to answer an earlier question, this is not a perfect square. Yes, so you cannot square root both sides here. So you do need to factor everybody out and then multiply it across. So let us do that. Shall we see how our math goes here? So we'll start with, I'm going to do the top first. I'm just going to do the top first, then the bottom, then kind of put them all together. So we'll just kind of put a little squiggly there. All right, up on top, on this side here, we got basically 0.0224 plus 2x, and that is twice, so 0.224 plus 2x. If you factor, you FOIL, whatever they call it these days, you will get this here, 0.00050,176 plus 0.0448x plus 0.0448x plus a little 4x squared as you go in and out on both of those. Does sound good right about now, but if you do the math in and out there, we get those guys. Combining these sort of middle terms here will get us for the top there something that looks like 4x squared plus 0.0896x plus 0.00050,176. Any questions on that so far? I'm going to do the same thing here for the bottom. So I'm going to flip a page here and basically factor out the bottom there. So let me drop here a color here. So doing the bottom there, we got, bottom we had 0.00623 minus x and 0.00414 minus x. Obviously, that's the bottom here. Again, we're going to go in and out on that. And if you do that, you will end up with 0.000025792 minus 0.00623x. Minus 0.00414x and a plus x squared. Once again, comboing those guys together will give us for the bottom here x squared minus 0.01037x plus 0.0000. Really should use a little scientific notation, but oh well. I just feel like writing zeros today. So that's going to be the bottom there. Yes. All right, now I got the top, I got the bottom. I'm going to put them back together and finish the rest of that there. So we'll go here on the top. We had there on the top. Where did it go? There it is. We had 4x squared plus 0.0896x plus 0.000500176 divided by our bottom, which was x squared minus 0.0137x plus 0.1234. And that's going to equal 54.3. We're obviously at this point going to multiply what's on the bottom to the other side. Now, everything on top was not touched, so I'm just going to recopy the top just the way it was since we didn't touch it. 4x squared plus 0.0896x plus 0.000500176. Again, basically taking 54.3 times each of those will give us 54.3x squared minus 0.56309x plus 0.00. It's 1401. Almost there. So we're going to now combine everybody to one side. I chose to take everybody on this side and move it over here just to keep my x squared positive. It really doesn't matter, as I mentioned earlier. And if you bring everybody to the other side, that should give you a final equation of 50.3x squared minus 0.65269x plus 0.000899 equals 0. We obviously would subtract that to the other side, subtract that to the other side, and subtract that to the other side, it looks like in each of those cases, yeah. Any questions up to there? Just to show you, I did do it on my paper here, yeah. There you go. All right. That's my A, B, and C finally. I need a nap after that, but that's still A, B, and C at that point. If you're still doing this problem and haven't moved on to the next one, we're going to put that into the quadratic at this point, right? So we're going to go into that x is equal to minus b plus or minus our square root, b squared minus 4ac divided by 2a there. I'm going to flop it to the next page here, I think. All right. So putting those numbers in, that will give us an x is equal to 0.65269 plus or minus the square root. Again, if you do everything inside the square root, I believe you should end up with 0.24513. And then if you take the square root of it, 0.4951. Again, with rounding, should be somewhere in the ballpark there. And 2 times a should give you 100.6. This again is going to give us our two x values. X is equal to, doing the plus here, 0.0114. Or if we do the minus, it will give us 0.001567. So just to rewrite our equilibrium line here for our H2, our I2, and our HI. Our equilibrium line there from our ice table was 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. So looking at these numbers here, to me, this guy looks a little too big, yeah? And that's not going to work so well, as we would get a negative number, obviously, if we put that in there. So that will leave this guy here as our winner. So going here, that would get us 0.00623 minus 0.001567. And that will get us for our H2 0.004, I think it's 663 molar for the H2. Doing the same thing here, 0.00414 minus 0.001567. Gonna get us for our I2 0.002573. Probably could have killed a significant figure there at the end, I imagine. And lastly here for my HI, gonna give me 0.0224. Remember, it is plus 2 times my X value of 0.001567. And that's gonna get me some really bad writing there, 0.0255. We'll call it 3 molar for my NH3. Again, perhaps this one a little bit more complicated, as I mentioned, might want to check. So let's see. If we take my 0.02553 and I square it by putting it back into my equilibrium expression, divided by 0.004663 and divided by 0.002573, that's about a 54.3. I'm going to go with that. Seems good. That's not that point. Any questions on that? I would say that's a little bit more complicated. Yes. No, you could have multiples on both sides. But if you're talking about are you talking about the doing the quadratic in terms of that, or? No, in general, you could use for any equilibrium reaction. So the first one we did that I did had just one on each side. This has obviously 2 and 3, but you could have 2 on each side as well, and it works. It would work it would kind of work the same way. So yeah, so you would factor it out and kind of put it in there. Yeah. Yeah. You would just factor out the top, kind of like what I did here in a sense. Yeah. We're gonna talk about a couple other examples next time as well, some ways to solve it, but you will have a way to solve it, basically. Yeah. Other questions? All right, so we've seen a perfect square way of solving. We've seen a couple quadratic ways as well. There are a couple other ways to sort of solve these type of problems, which we will talk about next time. One way that we will not do, which is known as successive approximation. So we will not do that in these type of problems, but sometimes books like to solve problems that way. And what successive approximation essentially is basically you know that the X value has got to be smaller than, say, that guy's number in front of it. So you pick an X value that's smaller and you put it into like your equilibrium expression and you leave this X alone and you solve for it. And then if the number you get out is the same one you put in, then you're done. If not, then you take the number you got, put it back in, and you keep going until the number you put in is the same number you get out. Can be an all-day project if you're really crappy at it. So we will not do that. But just so you know, if you happen to see it in a book, sometimes they'll do successive approximation that way as well. All right, any questions on that? Yeah. Yeah. Would I just give you whole numbers? It depends. It really does depend. I don't know. When I make up the numbers when I do in the problems, though, it kind of depends. So they won't always be nice, pretty numbers. You may have some decimal numbers. So you should be able to do it. By the way, you do need to show work. Yeah. So you got to show some work here. It also includes, by the way, the final step here. Yeah. Can't just like plug it into your calculator and let it do the quadratic for you, right? So you got to show some work along the way. Yeah. Even if you do plug it into your calculator to get the quadratic done for you, you got to show